Hey, this is Brock Lemiers, and in this video I want to talk about what's next in electrical and computer engineering. This is kind of the wrap up to this series on Introduction to Electrical Engineering. And what I want to do is kind of break down the field into kind of its broad categories and then talk about what the challenges are looking forward into the next 20 years and the type of careers that are going to be needed by our society. So we kind of started this series by trying to answer this question of what is electrical engineering? And it's not a question that you can answer really quickly, okay? Because you have to dig deep to actually understand some of the principles of electricity and magnetism before you can actually then expand that out and talk about what those applications are used for, okay? And so really the point of this was to expose you to how electrical engineering is used in society, but we had to go deeper into what things are. So you have to get a basic background of the principles of electrical engineering. And so we have to talk about things like obviously charge and moving charge, but then you have to go through all the discoveries that were made, the Michael Faraday, moving charge through a magnetic field and it experiences a force. So then that turns into, we can make a motor, and then you start doing it backwards and make a generator, and then the whole discovery of electromagnetic radiation as a particle and a wave, and then that becomes light, and then we discover that those electromagnetic waves exist at all different frequencies. So now we have things like infrared and microwave and ultraviolet and all this sort of stuff, and then we have to look at like materials, semiconductor materials, and how we can manipulate them to build circuits that do certain things. So we had to get the background of kind of just a broad sweep of what are the key scientific discoveries that we use in electrical engineering to build the systems that we use in our society. So you can't answer the question of what electrical engineering is without going into some background. Now, the trick of going into the background is how deep do you go, right? I mean, because you can spend your entire career getting, learning the details of all the different types of things that are in electrical engineering. But in general, it is broken down into electricity, the movement of electrons through things and trying to control that. And then it also is the forces, the interaction between force and magnetic fields. So that gives rise to the machines. And then that also gives rise to electromagnetic waves. So those kind of principles of discovery are kind of the guiding force behind electrical engineering, and then we break it down further from there. Okay, so then hopefully as we go through this, you start seeing these discoveries transition into applications and systems that we have, so you get to understand the types of topics that we want to cover when we teach electrical engineering at a university. Okay, it's you can't just stop right here. You got to go deeper into all of these areas. Okay, and then as you decide what you want to do, you start specializing and learn even more about it. And then that leads you finally into kind of careers, right? So then you finally start looking into the industry, looking into society and saying, where can I use these skills? Where can I work? What are the industries that use it? And even answering that question is very difficult because electrical engineering is, electricity is ubiquitous, right? Computers are ubiquitous. There's nothing that doesn't use electricity in society. There's nothing that doesn't have a computer in it. So you can't, sometimes you say, well, I have an industry such as electrical power, and so you wouldn't think that an electrical engineer would work in computers. And it's like, well, no. They also work in computers. And it's like, well, what about aerospace? And it's like, yeah, they work in there too because there's computers. And so it's one of these things where there are actually fields, like electrical power that is considered an industry you can work in, but there's also just electrical engineers work in every single industry, okay? Okay, so as we go through this, the other goal that I had was to give you a small set of basic skills, okay? It's one thing to sit here and listen to me do PowerPoint for 4 months and then walk away and be like, I can't even do anything, right? So you may not have even noticed it, but you did build up a set of basic skills. Okay, so let's go a little bit further here. Let's begin by breaking down electrical engineering into categories of basically kind of like the fields within electrical engineering. And this is very broad because it is so difficult to do, but we'll give it a shot, okay? Okay, so the first field is usually power and energy, okay? So this is where, we figured out that if you move charge or you move a conductor through a magnetic field, charge will flow, Michael Faraday's law of induction, and this gave rise to machines. Okay, so generators and motors, and we basically use it to build the electrical power grid. And so power tends to talk about the electricity that runs through wires across our nation and across the planet. Okay, energy is the term where we're trying to figure out ways to get our electricity, to generate electricity without burning fossil fuel. Okay, so remember, natural gas and coal are where we get almost all of our energy from, and that can be bad sometimes. A lot of smoke in the air, a lot of global warming. So this field right here has all to do with that. Now, working in this field, you need to understand how machines work. You need to understand distribution. You also need to understand the economy of it all. So, like, how do you get the pricing of electricity to, where it's affordable? How do you manage all these new sources of energy coming online? And just basically researching what are future sources of energy and how can we use them to get off of fossil fuels. Okay, the next field is I call it microelectronics and semiconductors. Microelectronics, it's kind of a catch-all for circuit design. Okay, so you know that we have circuits everywhere. All the electronics that you see, your phone, microphones, cameras, thermostats, TVs, there's circuitry in there. Okay, you have electricity that comes in. There are circuits that process that and use the electricity to do stuff for us. Okay, and so that whole field is kind of like circuit design, but it's microelectronics, and it's also semiconductors because we build all of our circuitry on. Let's face it, semiconductors. So all the computer chips, every digital processing chip, they're all built on semiconductors. So you have to kind of understand the semiconductor behavior. But then semiconductors in itself is a massive, massive field because this is like, you've probably seen pictures of people in the bunny suits, right? So they're in a clean room and they've got these wafers of silicon and they're doing all these processing steps to them to make the transistors and resistors and capacitors that build our circuits. That in itself is a massive, massive field because it's very difficult to make those chips, and you have to spend a lot of money to do it, to build the plants that actually can process these chips. And then what happens is you make tons of them. It's not like you make 3 or 4 a month. You're making 20 to 50,000 chips a month. And so it's this huge statistical processing component of trying to figure out failures and it's just awesome. Okay. So the microelectronics and semiconductor is an entire industry in itself, and that's considered electrical engineering. The other one, computer engineering. So computers are everywhere. All right, let's just face it. There's nothing that exists anymore that doesn't have a computer in it. And so what does an electrical engineer do within computers? Well, it's a field within electrical engineering called computer engineering. And it really is where you focus on the hardware, the low-level hardware that are used to build computers, and also the low-level software. So you, as a computer engineer, you're the bridge between hardware and software. Now, a computer scientist is the person that's going to come along and write higher level abstract software that runs on top of this computer hardware that, does a lot more advanced stuff. Okay. But somebody has to be at the low level that's actually building the computing hardware and understanding the low level operation. Now, computer engineering you can kind of fall into a couple different categories. Number one, you could be kind of basically like what you would think about laptops and servers. So high-end computers, like Intel and AMD and stuff like that. But you also have embedded computers. And it turns out that embedded computers is a much bigger field. For reference, I think in 2018, it was like there was 300 million computers sold in the form of like workstations and laptops. There were 30 billion embedded computers sold. So embedded computers are the ones that are in everything. They're in your mouse and in your microphone, in your car mirrors. They're the ones that control the small electronics that are everywhere in our lives. So these are two kind of fields that you can work in as a computer engineer. Okay, then there's the electromagnetic waves. We're going to group this as optics and communications. Huge field. This is just massive. We've talked about electromagnetic waves, and we talk about the spectrum that they can exist in. And some of those waves have wavelengths that we can see with the human eye, and that is an optical thing, right? So it's stuff you can see. But optics, usually you'll say like optics and photonics to describe that we're talking about all the different waves, okay? So we're talking about microwave and radio and X-ray and all that sort of stuff. But optics in itself, you can use it for a whole bunch of different applications. So you can build lasers, and you can range with it. You can do sensing, remote sensing. You can shoot it at something and try to determine the material and how far away it is and stuff like that. But you also use it for communications. Okay, so you have optical fiber that's laid across our planet, and we basically shoot photons or laser beams down this, and we use it to communicate back and forth. Along that same kind of line of thinking, this is also where radio waves are used too. Remember, they're both electromagnetic waves. They're just at different frequencies, and they just experience different behaviors depending on the atmosphere they're in. And so this is also where you would be working as, on like the 5G network or the 6G network or the 10G network, and also just anything with wireless communication. So any Wi-Fi, any sort of digital communication. We lump it all together because it really is based on electromagnetic wave propagation. Okay, so that's why we kind of lump these together. But huge field. And then finally, we have this other one that we haven't really talked about, but signals and controls. So the electrical signals that move through circuits, they carry information, right? And when you think about a sine wave or a DC signal, it's not very interesting, right? It's like, how can that convey information? Well, when you talk about signals or signal processing, it's all about trying to understand how to manipulate the electrical signals and make them, basically convey information, lots of information. And so it's a lot of math. It's a lot of discrete math. It's a lot of transforms. This is where you hear like Laplace transforms and Fourier transforms and stuff like that. But it's the whole kind of the understanding of how to manipulate signals and then demanipulate or basically decode signals so that you can extract the same information or the same information that was sent. So that's a whole field. And then we lump it into this. I don't know if this is fair or not, but this whole thing called controls. Okay, so controls is control engineering or control theory. It's where you control something, obviously, but it's where you have a sensor of some sort where you can tell, for example, a machine or a motor or an arm to move a certain way, and then you watch it moving, and based upon how fast it's moving and how close it is to where you want to be, you can automatically adjust the motor control to like slow it down and stop it. So what this is it's automatic control, automated control of some motor, okay, or some moving part. Now this, you can think about it, this is like everywhere, right? So this is like space shuttle, the rockets, they have to have like electrical systems that can automatically adjust and accommodate, changes in the environment around them. You can think about robotic arms, if you're moving, you can't just move 100 miles an hour and slam into something. You got to like know where you're at, know where to slow down. So it's, the reason we lump them together is because the signals and controls, it's all based upon a lot of math, okay, a lot of linear algebra and a lot of algorithms to understand how to basically send the right signals into a system in order to get the right output. Okay, so that's what we call signals and controls. Now these are just 5 broad topics, and you can, there's probably people that would add more to this, but this is just in general kind of 5 broad topics. So let's talk about challenges going forward in each of these areas. And this is just a high level version of it, but let's start with power and energy. So what are the challenges in the next couple decades that you need to face? First and foremost, fossil fuels, right? I mean, we talked about how when you burn fossil fuels, it puts carbon emissions into the air, and that, it's gross, the sky isn't blue anymore, but more importantly, it's getting hit by all this electromagnetic radiation from space, and it heats up the atmosphere. So there has to be some major breakthrough in this area that either, number one, replaces fossil fuel but we can't give up electricity. Okay, you have to have the same amount of electricity or more. Or 2, figure out a way to not let the carbon emissions get up into the upper atmosphere. So they call that carbon sequestration. But there has to be some major, this is a huge challenge going forward. I mean, this is the planet killer here. So make sure you fix that one. Another one that is really interesting is electric cars. So right now, cars burn gasoline, and they also put out carbon emissions. And so there's this big movement to go to electric cars. I mean, they're awesome, right? I mean, they're faster, they're more torque, they're just great. But the energy is energy, right? So we've converted the cars to use electricity, but that electricity has to come from somewhere. So now just take a minute and think about all the cars in the world, and now take all that energy that is used to drive them and put it onto the electrical grid requirements. So the electrical grid is going to have to get drastically more powerful if we're going to be charging our cars from it. So you kind of move the problem from two things into one. So two things is we burn fossil fuel to power our electrical grid, and then we burn fossil fuels to power our cars. What we do now is we say, okay, we're going to get rid of the car fossil fuel usage, but then we push it all back onto the electrical grid. So how do you handle that? How do you manage that increased need for electricity? And then finally, there's this other thing that's kind of the smart grid. They use smart grid as the term to describe it. What it is where in the old days you had a power plant, so you're burning coal in Colstrip, Montana, and it powers cities, and then that's it. Okay, if the plant goes down, then there's no electricity. All right, and that was the model. Nowadays, what's happening is that there's all these different types of electrical energy generation that are being put onto the grid. So think about, you have solar cells. How do you get solar energy to be put back on the grid safely? Wind turbines. And then also, people have like small generation where like somebody's house, you'll have like solar panels on your house and you want to put that energy back into the grid. And universities might say, well, I want my own mini grid and I want to generate some of my electricity, and then if I have excess, I want to sell it back. But then if I run out of electricity, I want to use the grid. And so how do you manage this whole kind of new sources of electrical energy generation being connected and disconnected from the grid automatically? So that's one of the big challenges going forward in this area. Okay, so what about microelectronics and semiconductors? What are those challenges? Well, in general, it's kind of the same challenges that's always been in the semiconductor industry is how do you make transistors smaller? So we've reached a point now where we're down into the nanometer processing, meaning we're building structures that are like 10 nanometers and below in size. And it's becoming just incredibly expensive and incredibly difficult to do this. It's just, the yields are low. You're spending tons, billions of dollars to try to bring up these fabrication plants, and it's just really, really difficult to do that. And the need for processing is not going away; it's actually increasing. So that's probably the biggest challenge going forward is you're just reaching a point where you can't make these transistors smaller anymore, and you got to figure out a different way to do it. The other thing in this industry that is really interesting is recycling. What are you going to do? I just said earlier, 30 billion embedded computing chips were sold in 1 year. What are you going to do with all this stuff? We just throw it in the garbage. And it's like, you can't do that anymore because you're producing so much stuff. It's just going to overrun our planet. So this is a huge part that the semiconductor industry has to think about going forward, or you do anyway. So the next one, I'm going to group computer engineering and signals and controls together because they really are going to face kind of the same challenge. And the first one is just flat out big data, right? So when you hear the term big data, what it means is that there's so much information stored in a computer that humans can no longer manually process it, okay? There was a day where you could, click through files, if you had like 1,000 files on your computer, you could go through them one by one. It might take a while, but you can't, you could. Nowadays, you're talking about trillions and trillions of files, and it's being generated every second of the day by everybody on planet Earth, and there's just no way that you could ever even determine which files to open. You have to do it with an automated algorithm, so some sort of software. And so that is a huge challenge because data is being generated like crazy. Everybody's taking pictures and uploading videos, and it's all being stored somewhere on these massive servers, and you have to figure out ways to process this. So within computer engineering, it's how do you come up with the software and the algorithms to manage all that data, and how do you actually use it? How do you process it? It's mind-boggling. And then going along side by side with big data is cybersecurity. So now you think about attacking a country or attacking a business. Everything uses electricity. Everything is based on a computer. Everybody has so much data they can't even manage it anymore. So the attacks that occur today tend to be cybersecurity attacks. So this is one of the biggest challenges that every nation faces, because we rely so much on, our automated systems, our electrical systems, and if they're computers, people can try to hack them. Okay, and so cybersecurity is one of these big challenges. I say signals and controls are lumped into this because the signal processing algorithms are also part of this. It's like they are used to understand and generate and interpret big data. They're also critical to trying to identify attacks, cyber attacks. So you look at patterns in the data, and controls is lumped into here too, because you think about attacking a country or attacking a city. What do you do if you're not going to shoot a missile at it? Well, why don't you just take the electricity away and everybody dies, right? And so you might want to try to hack into the power plants and turn off the electricity. And so this is the control mechanism. So all the relays in the electrical power grid, all the HVAC systems that keep the plant running, all these different things. So signals, controls, and are embedded within this whole issue of cybersecurity. So then what are some of the challenges for optics and communications? Okay, so more, right? I mean, big data drives this, but think about like the 5G network coming on board. Why do we need another network? It's because we just need so much data transmitted. And when we think about 5G, it's wireless communication, so it's radio waves, okay? But it all feeds this optical network that lives underneath our cities that actually can transfer the information far distances. And so there's so much need for just more communication, what we call bandwidth. And it's in all areas, okay? So there's the wireless, so there's going to be a 5G, there'll be a 6G, there's more wavelengths that we can use to transmit information, but it's also the optical fibers that we use to communicate. So it's just data. How do you do it? How do you get more? And then another one is imaging. This is one of the things that's really happening is, so as optical systems become smaller and smaller and more compact and you're able to just process data more, we're starting to use them to do what we call remote sensing and remote imaging. And this is great. So you think about like x-rays, we were able to once see into the bones or see your bones. Well, now you can have even more advanced imaging systems that can see tissues. And how does that progress going forward? It's going to allow us to look into our brains and into our biology to try to figure out what's happening. It's also going to allow us to do things like spy, right? I mean, it's you're going to be able to see through walls, and can you make invisibility cloaks and things like that. So there's a lot of military and military applications that are kind of spooky, but it's just that whole field of imaging and looking inside and trying to understand what is actually going on beyond what you can see with your eyes. And then of course that has applications in earth imaging. So can we in real time watch what's happening on our planet with respect to weather and respect to seasonal patterns and earth, just dirt running away from erosion and all this stuff. So once you can unlock that, you can actually see a bigger picture of what's happening and make real time decisions. So it's just so much awesome stuff in this field. Okay, so as we wrap up, what does the future hold? Right? And nobody knows. But you could go back 20 years ago. They wrote this report called the Engineer of 2020, because they're always trying to figure out, like, what are the skills that engineers will need 2 decades from now to try to meet the challenges that we think we'll see. And they did a pretty good job, because the biggest thing that they came out with in this report was that engineers wouldn't be so siloed in their disciplines anymore. It wouldn't just be like, I'm an electrical engineer, I work for an electrical engineering company, and I only do electrical engineering, I do this circuit design. You're going to work on interdisciplinary teams, and you need to be able to communicate with other people. And it's not just, electricals and mechanicals working together. It's like electricals and business and electricals and, government officials and stuff like that. And I would say that it is very true what they predicted. It's when you think about, if you're a computer engineer and you go, what kind of company do I work for? And the answer is, every single company that does anything to do with tech development. It doesn't matter what it is. It could be power, it could be social media, it could be anything, because you're working on all these interdisciplinary teams, because all the solutions that we have today, or all the products, systems, they're all interdisciplinary. So that was a very good prediction. So then going forward, what is it? People don't know, right? I mean, you can't even imagine the amount of technology that's going to be invented in the next 20 years. I have my own ideas on it. I'll just share a couple of them. I think one of the things that's going to happen is there's going to be different pathways into engineering. So right now we think of an engineer, electrical engineer, as you got to take 4 semesters of calculus, then you take 3 semesters of science, 4 semesters of science, and then you do circuits 1, circuits 2, electronics. And I just feel like there's going to be such a need for people that think like engineers, specifically electrical engineers, that don't need to go through all this calculus. Okay, and so it's a different type of electrical engineer, right? They're not going to be able to design circuits. They're not going to be able to do the in-depth signal processing. But there's a need for people that understand electrical systems at a higher level and can make decisions and manage projects. So I think that the engineer of 2040 is going to be a little bit different in terms of a workforce. You're just going to have a wider variety of types of people that call themselves electrical and computer engineers. The other thing is the rapid education. Okay, so right now, think about it right now. You need to know something, you just Google it or watch a video on YouTube. And 20 years ago, you didn't do that at all. And so what's it going to be like in 20 years? We're going to have, exponentially more information that you have to access rapidly. How are you going to do it? Even a YouTube video is going to be too slow. So this is where things like augmented reality and computer assisted learning and just computer assisted thinking is going to be something that's going to be really prevalent. So how do you design an electrical system and just be pulling in this information that's being almost created in real time? And then we really are just heading for a precipice with our planet. I mean, there's no way around it. If electrical engineers don't figure something out with all the other people on Earth, we're going to have a problem, okay? So once we turn that corner and we figure out how to, reverse global warming and get off of fossil fuels or sequester the carbon, things are going to look a lot different. I mean, just imagine in 20 years, we're going to have electric vehicles, okay? We're going to have clean energy. Everybody's going to have water. Everybody's going to have food. Everybody's going to be healthy. It's going to be awesome. Life is going to be so good. And it's solely due to electrical engineers. No, I'm kidding. You're going to play a critical role in the future. And it's an exciting time to be alive. And it's going to be exciting to see what the future holds. So I'm going to leave it with that, and I'll just say finally 2 things. Number 1, good luck. Society needs you. And 2, where are the flying cars? Okay, we'll see you later. Bye.